population means. Yesterday we talked about proportions. They work almost exactly the same. So if in your paragraph they talk about 150 out of 200, you know that you're talking about a proportion because you get a decimal or a percentage of success. If instead they tell you about a mean, then we use the following procedure. Works almost exactly the same. There are a few slight differences. So the first big thing is that you'll notice that we're going to be taking one sample z intervals for means, first of all. The second thing that you'll notice is that when you look at estimating your interval, you're going to have the mean plus or minus your z-score times the standard deviation over the square root of n. And if you remember the standard deviation over the square root of n was when we're talking about samples instead of just the standard deviation. And so that's how we talk about our margin of error. So this thing over here, later on, we're going to be talking about this plus or minus thing. That's our margin of error. Okay, so we're going to, just like in the past, we take our simple random sample of size n from our population. It has an unknown mean, mu, instead of proportion, p. And it has a known standard deviation, sigma. As long as it's normal and independent, our confidence interval is x bar, which is our mean of the sample, plus or minus the z-score, times the standard deviation over the square root of n. When we're choosing the sample size, we need to make sure we're also checking for the margin of error. Oftentimes, like in the past stuff, we talk about our margin of error, and we want that margin of error to be less than or equal to a certain value. It'd be really nice if you guys were not doing that while I'm doing this. And that, again, is our z-score times sigma over the square root of n. So this works just like yesterday when we were doing this margin of error thing. The formula is a little bit different, but the procedure is the same. Down below, for example, administrators at our school want to estimate how much time students spend on homework on average during a typical week. They want to estimate mu at the 90% confidence level with a margin of error of at most 30 minutes. Notice they're not talking about a decimal, they're talking about a number value. A pilot study indicates that the standard deviation is 154 minutes. Holy Hannah. How many students need to be surveyed to estimate the mean number of minutes spent on homework per week with a 90% confidence and a margin of error of at most 30 minutes? So in order to find this margin of error thing that we were talking about just a few seconds ago, we take our z-score for 90% confidence interval. Remember that when you're talking about a 90% confidence interval, what you're talking about is the stuff in here where it's blank, not shaded. So you're actually looking at 95 on the z-scores because you want 5% on either side. So be careful about that. You can either, again, memorize the number or know how to find it in your table. One of the two. That number, when we look at our z-scores, we have z times sigma over the square root of n, and we want that to be less than or equal to our margin of error, which in our case here, when we write it out, our z-score for the 90% confidence interval is 1.645, and then times our standard deviation, which they told us was 154, divided by the square root of our sample size, and our sample size was, we don't know, and they want that to be less than or equal to our margin of error, which is 30 minutes. So you'd multiply, I would multiply both sides by the square root of n and then divide by 30, and when you do that, you find out that your n has to be greater than or equal to 71.3067. And then when you put it in the context, you would have to have at least a sample of 72 students to estimate mu at the 90% confidence interval with a margin of error of at most 30 minutes for how much time students spend on their homework on average. So on this next slide, the whole point of this slide is talking about what a t-interval is. So one of the other things we can do is we can take this one sample t interval for means. This happens only when we don't know sigma. Super important. For sure, highlight the blue. That's when you use your t interval. If you know sigma, you don't do t, you do z. If you don't know it, then you have to do the t. Okay, so how does it work? The density curves of this t distribution are very similar to our standard normal curve. They're symmetric, about 0. They're single peaked, meaning it looks like a normal distribution, and bell-shaped. The spread is a little bit more than t, or than z, excuse me. And the t distributions below have more probability in the tail. So in a normal distribution, you have that high peak in the middle, tails on either side. The t distribution, the peak will be lower than your z, which means that there is a higher tail end. So our tails are kind of low on the ends for the z. The t is a little bit higher. They talk about one other thing in t that's a little bit important to know when you're doing your distributions, and that is, what is the degree of freedom? So the degree of freedom is always n minus 1. So if you take a sample size of 100, then your degrees of freedom is 99. So in our picture up here on the board, what you'll notice is our z interval is this red line right here. This is our z distribution. If I were to take a t distribution with 2 degrees of freedom, you'll notice that the tails in the light blue are higher than the tails in the red for our z. That means that there's more probability of it happening in the tails, and our peak is lower. As my degrees of freedom, so this was 2 degrees of freedom, and the red was our regular z or normal curve. As I increase the degrees of freedom in my distribution, what I notice is that my t distribution becomes much closer to my standard normal curve, or my z. So you can see in the gray here how it's above the blue but below the red for the peak, and the tails are below the blue but above the red. So the bigger the sample size, what this is saying is the bigger your sample size, the closer your t distribution looks just like the standard normal curve. So you want, as always, a big sample if possible. That's all it's saying. Otherwise, the t works very similarly to the z-score situation with means. So our formula over here for this t distribution is still the mean plus or minus, but now instead of a z-score, you're going to use a t-score, and then the okay, so in this t interval, we have the formula, but we use a t-score instead. And just like in our z, t is going to be the critical value. It's going to come off your table. It's table B out of your stapled packet. You'll have to look at that. And we use it only when, number 1, our population is approximately normal, and the sample size is at least 30, and the population has to be at least 10 times the sample. That was our n is less than or equal to, or yeah, n is less than or equal to 10n, whatever. And then our confidence interval, we do the same thing as we had in the z-scores. Number 1, we're going to state what we're going to do. We want to find a blank % confidence interval for the true population. And this time it's going to be a mean instead of proportion of whatever the context of the problem is. Number 2, we're going to plan. That's where you put in the stuff about it being independent. It's simple random sample. It's normal. Those are our conditions. We use the central limit theorem that we talked about earlier, where the sample size is greater than or equal to 30, so we don't have to worry about what happened with the population. And then if we show that our population is at least 10 times our sample, we know that things are independent. And then we actually calculate this confidence interval. That's the formula, the x bar plus or minus t sigma over square root of n, and then we draw our conclusion put into the context of the problem. That works exactly like we did yesterday. So let's try a couple examples. First one. Actually, this example probably won't have all of this stuff, but Suppose you want to construct a 90% confidence interval for the mean of a normal population based on a simple random sample of size 10. What critical t-value should you use? So before you do this, you need to go into your packet. So pull out your white packet so you can see how this works. And I'll show you on the board as well. And we know that we want a 90% confidence interval. Something that's really important that we talked about on a previous slide is you need to know that your degrees of freedom is going to be equal to whatever your sample size is minus 1. So that's 9. And I want you to find the t-value. So find the t-value. See if you can figure that out from the table. This is table B. Okay, so in this one, this is just to get you familiar with that T table, which is actually, we find out in our staple packet together, is C, table C. So for the 90% confidence interval, the degrees of freedom are 9. If you look down below and you look for where it says 90% confidence interval, look up, you'll see 1.833. That is your T value. You'll be able to use your stapled white packet on the exams, of course. And it's what they also provide you on the test for the AP exam. So here is a full example where we're going to go through the 4 steps in number 2. And we see here as a part of the final project in AP Stats, Christina and Rachel randomly select 18 rolls of a generic brand of toilet paper. I like Charmin Strong. And measure how well this brand can absorb water. I don't really know why that's important. To do this, they poured a quarter cup of water onto a hard surface and counted how many squares it took to completely absorb this water. The results are stated below. Let's construct and interpret a 99% confidence interval for mu is the mean number of squares of generic toilet paper needed to absorb 1/4 cup of water. So here we go. First, we state what's going to happen. So, we want to find a 99% confidence interval for the true, and this time it's mean, not proportion, mean of toilet paper needed to absorb a quarter cup of water. We're going to plan what's going to happen. So we will do a 1 sample T interval for mu since sigma is unknown. We don't know the standard deviation. We have a random sample of 18 because that was stated. And when we look at normalness, since n is 18 and not greater than or equal to 30, we should check to see the normalness of this. Now there are a couple ways that you could do this. You could type this into your calculator. You could create a box and whisker plot with the outliers if you want to. You can do a few other things. You can use your stats on there. Some kind of visual will help the reader understand that you understand what's going on.